Okay, we're working on 11.3, the B and C level problems. So for number 21, they give you a picture, and here it is. You have an isosceles trapezoid, and what you know is that this angle here is 40, and that each of these sides are 10, and then this base here is 6. All right, so the first thing is that I am going to make a height here. So I'm going to drop a perpendicular here, drop one here. Now I know I have a rectangle here, and so if this is 6, then its opposite side is also 6. All right, so that's good to know. Now, since it's an isosceles trapezoid, this triangle here and this triangle here are the same. They're congruent. So if this value, if this length is x, then this length is also going to be x. And so this entire length of this base is 6 plus 2x. And I don't know this base, which I have to find, and I don't know the height, which I have to find. So let's first find the height. Okay? I've recopied this little triangle over here. This guy right here. I've copied it to here. So let's look over here now. If 40 is my reference angle, then h, the height that I'm trying to find, is opposite the angle 40, and 10 is the hypotenuse. So the trig function that deals with opposites and hypotenuse is sine. So I write myself an equation, sine of 40 equals h over 10. Multiply both sides by 10 to get 10 sine 40 equals h. Well, sine 40 just happens to be 0.6428, and when multiplied by 10 gives me 6.428. That's the height. Okay, so the height of this isosceles trapezoid is 6.428. Now I also need to find this x value here. All right, so let's do that next. Using this same little triangle and the same reference angle, the cosine of 40 is x over 10, with x being the adjacent side and 10 being the hypotenuse. A and h for adjacent and hypotenuse. ADJ, hype. Okay, so cosine of the reference angle 40 is equal to x, the adjacent side, over 10, the hypotenuse. So again, multiplying both sides by 10, I get that x is equal to 10 cosine 40. The cosine of 40 happens to be 0.7660. When I multiply that by 10, I get 7.660. So that's my x length. So this entire length, now I have enough information to figure out my base. So it's going to be 6 plus 2x like we said before, but because I know that x is 7.660, I do 6 plus 2 times that for a grand total of 21.32. Now we have enough information to figure out what the area is. The area of the trapezoid is 1/2 the base 1 plus base 2 times the height. So one base that we just figured out, 21.32, the second base was 6. Times the height, 6.428. So when you get that all done, you get 87.80, blah, blah, blah. And it says round to the nearest tenth, so that's 87.8. Okay, so that is 21. Moving on to 24. 24 is a really difficult problem. Probably should not have put that on the homework, but it's there, so let me give you the explanation here. All right. The first, the A and the C part are actually reasonable problems. It's the B part of this problem that is really a pain. So let's look at this here. Okay, what you have to do is we've got to look at the area of triangle ABD. So that's this guy right here, ABD. And we have to compare it with triangle ABC. All right, so this one we can do fairly easily. We know that the area of any triangle is 1/2 base times the height. And I know that this base for ADB is 12. All right. I also know that the base for ABC is also 12. So they have the same bases, and the height for both of those triangles is the same as well. If I drop this perpendicular, this guy is a height for ABD. You can see that. And this guy, you know, is the height for ABC. And remember, of course, these are my two parallel lines, and so the distance between them is always the same. All right, let me get this straightened up a little bit here. Okay, so the area of ABD, 1/2 the base times the height, which we don't know, so I'm just going to leave it as a variable. The area of ABC, 1/2 the base, 12 times the height, which I don't know, but I know that it's the same as this height. So I'm going to just leave it the variable h. And so this guy has an area of 6h. This guy has an area of 6h. And when I compare the area of ABD, triangle ABD, to the area of triangle ABC, it's 6h divided by 6h, and that's a 1-to-1. Okay. I think I'll do C next. Okay, so for C, let's look at this part. We have ABD. All right, I need to compare the area of ABD, and I need to compare the area of triangle ADC. So that's this little guy. So this whole big guy, ABD and ADC. All right, so I know that the area for each triangle is 1/2 base times the height. And so for ABD, the base here is 12. The height is, I'm going to just call it h. All right, so for a grand area of 6h, my 2 and my 12 cancel, gives me 6h, units squared, of course. And ADC, you know, the base here is 4, and the height is the same. The height is the same as this other height because these two bases are the same distance apart. One has a base of 12, the other has a base of 4. But the height, the distance between the two bases, the altitude, is the same for both triangles. So I can use the same variable to represent the height in both cases. So 1/2 the base, in this case ADC has a base of 4 times the height. So this is 2h. So what I have to compare is this area 6h to this area 2h. And I get a 3-to-1 ratio. So that's good. All right, so the tricky part comes with part B. So let's go back here. We had to do some preliminary work here for part B. All right, so here we go with the preliminary work. All right, I want you to notice that triangle ABD and BAC, these triangles are both congruent. ABD congruent to BAC. Why is that? By side angle side. Now think about it. They both have sides that are congruent. It's an isosceles trapezoid. They both have the same base. And we also know that the base angles of an isosceles trapezoid are congruent. So for this triangle, I've got the side DA, I've got this angle here, this entire angle A, and then I've got this side AB. For this other triangle, BAC, I've got the side BC, I've got this entire base angle of my isosceles trapezoid, and then I've got this side AB. So we can see that the two triangles are congruent by side angle side. Now, that's good to know. So we also, since angle DAB is congruent to CBA, and I know that CAB is congruent to DBA because those triangles are congruent, then I can just subtract angle CBA from DAB. So take a look at this. Here's how this works. DAB, you know, somewhere out here, and my C is somewhere out here. Okay? So what I'm saying is I've got the whole big angle congruent, DAB, and I also have CA congruent. And so when I subtract this big angle DAB from CAB, what's left is this angle, DAC, right here, this guy with the star. So I have DAC congruent to CBD by the same reasoning on the other side. Okay? So what I have is that this angle here, DAC, congruent to CBD by subtraction. That's good to know because, okay, I have these two angles congruent. These two angles are congruent, they're vertical angles, and these two sides are congruent because they're the sides of the isosceles trapezoid. So I have this triangle, DAO and CBO are congruent. we do know that congruent triangles have the same areas. So if their areas are the same, then the ratio is 1 to 1. Now that is really tricky. That was a very hard problem. Okay, this next problem, number 26, is a little bit tricky, but it's kind of a fun one. Okay, so for 26, you have an isosceles trapezoid with bases 12 and 16 inscribed in a circle of radius 10. The center of the circle lies in the interior of the trapezoid. Find the areas of the trapezoid. Okay, so I drew a lousy circle here. Here's my interior of the circle. This is my center of the circle. All right, and I know that it's an isosceles trapezoid, and the radius is 10. So look, if I draw from radius here to vertex there, and I do the same here, I just want us to look at this triangle right here. Now, I'm given that the radius is 10. I don't know the height. I need to find the height. But I know that this entire length of this one base is 12. Now, if I drop the perpendicular, I hit the midpoint, right? And so this has to be 6, this has to be 6, because this is a midpoint. Now, pretend I don't know that this is 8. I have a 6 triangle, and I have a leg is 6, and the hypotenuse is 10. You recognize that. It's a Pythagorean triple, 6, 8, 10. If you didn't know that, you could say 6 squared plus x squared equals 10 squared, and then just solve for x. So we know from here, the center to this chord right here is 8 units long. Now let's look at this distance here, and admittedly my picture is pretty lousy and it's not to scale. So I know that this entire length here, from this base of the isosceles trapezoid, from this point on the circumference to this point on the circumference, is 16. Okay, and if I draw the radii, again I have an isosceles triangle. All right, this is a midpoint right here, just like before. So if the whole length is 16, this piece here is 8, and this piece here is 8. And so again, this is a right angle right here, and so I have a 6, 8, 10 triangle. So this height is 6 right here. Like I said, it's a lousy drawing, not to scale. So this height is 6, this height is 8, and so the entire height of the trapezoid is 14. Once I get that the height of the trapezoid is 14, I'm good to go with this formula. The area of the trapezoid is equals 1/2 base 1, 16, plus base 2, 12, times the height. So that's 28 times 7, which is 196 units squared. I think there's dust in this room, so I'm coughing so much. Blech. All right, problem number 29. 29 is not a hard problem, but it's got a lot of parts to it. So that's what makes this one hard. The individual pieces aren't too bad, but when you put them all together, it gets to be a little tricky. Okay, so for 29, you have this picture here. You have a trapezoid, and it's not an isosceles trapezoid. This angle here is 30. This angle here is 45. They tell you that this leg is 10, and this entire length is 20. So I have, I don't know the height. At this point, the height is unknown, all right? And this other leg is unknown. So really, I have to find the base, the second base, I'll call it B2. I have to find the second base, B2, and I have to find the height. That's what I'm looking for. All right, I think I called it a leg back there, but it's really a base. I know this. I know this. I know this angle's 30. I know this one's 45. It might help if you follow along in your book when you're watching this video. Okay, so the area of a trapezoid equals 1/2 the base, the sum of the bases. I know just this base only. I don't know the second base, and I don't know the height. I got to figure out the base and the height. Okay, so I want to look at this piece right here. All right, this is 30. This is 90, so this guy has to be 60. All right, so we know that the two 30, 60, 90 triangle. Well, this 30, 60, 90 triangle is similar to every other 30, 60, 90 triangle, and we know that the ratio of the sides is 1, radical 3, 2. 1 opposite the 30, radical 3 opposite the 60, 2 opposite the 90. Okay, so I just set up my proportions and solve. 10 to 2, there's my scale factor, equals h over 1. And so I can see that the height is 5. Then to solve for y, this length right here, I set up my scale factor, 10 to 2, and y over radical 3. And so when the smoke clears, I get that y is equal to 5 radical 3. Now, if you just knew that the ratio of the sides was in 1 radical 3, 2, you wouldn't have to go through all this. But, you know, I'm just doing a lot of detail here. Okay, so I know that the height is 5. If this height is 5, of course this height is 5 too, because they're both right angles, so these lines are parallel. And we know also that the distance between the two bases, which are parallel, is the same. So if this is 5, this has to be 5. Now that's good to know. And we had figured out that y, this portion from here, this vertex to this intersection here, that's 5 radical 3, that length. That's what that says, 5 radical 3. Now, this is a 45, 45, 90 triangle, and we know that the sides of 45, 45, 90 triangles are in the ratio of 1, 1, radical 2. We're not interested in this length, but we could find it out if we had to. What I need is this piece right here. Okay? So if this guy is 5, then this one has to be 5. I know this entire length is 20, so I need to know this piece right here in the middle, from here to here. Okay, and so this is going to be 20 minus 5, that's where the 15 comes from, minus 5 radical 3. All these pieces together have to add up to 20. 5 radical 3 plus 15 minus 5 radical 3 plus 5. Do they all add up to 20? You bet they do. 5 radical 3 minus 5 radical 3, that makes those guys go away, and then 15 plus 5 equals 20. So I know that I have this piece is right here. This is 15 minus 5 radical 3. So this base 2 is 15 minus 5 radical 3. Okay, now I have enough information to do this problem. 1/2 the area of the bases. Oh, what did I say? That's wrong. 1/2 the sum of the bases, 20, that's my one base, plus my other base is 15 minus 5 radical 3. 15 minus 5 radical 3 times the height. The height we figured was 5. Okay? 1/2 base 1 plus base 2 times 5. That's the area. All right, now it's just chunking out the algebra here. 20 plus 15 is 35 minus 5 radical 3. Can't combine anything like that. And then so this has to just stay like it is. Remember, treat radicals like x's. And then multiply 35 times 5, that's 175. And then 5 times 5 is 25. So I have 175 minus 25 radical 3 over 2. And that's units squared. So that is the end of problem number 29. Those last three were pretty stinking hard. All right. Okay, let's stop this now here. Oh no, where did it go?